This is video 2 of Unit 2, Lesson 4. We're starting at example 5. Find all the values of x for which the function is differentiable. So we need to look at where the breaks are in the piecewise function, because that's where we would have the breakdown of maybe a cusp or a jump discontinuity or something like that. So that's where we want to look. So we want to first look at x equals 0. So at x equals 0, we're going to take the limit as x approaches 0 from the left of the function, which is h of x, and that's going to equal the limit as x approaches 0 from the left of x plus 1 squared. So that's going to give us 1, and then we want to take the limit as x approaches 0 from the right, and that is going to be 2x plus 1. So when we substitute 0 in, we get 1. These are equal, so it is differentiable at 0. And the next point we have to check is at 3. So at x equals 3, we're going to do the limit as x approaches 3 from the left of h of x. So that's going to give us the limit as x approaches 3 from the left of 2x plus 1. And when we substitute, it looks like 2xh, 2x plus 1. And when we substitute 3 in, we get 7. And when we do the limit as x approaches 3 from the right, we're going to use 4 minus x squared. So we're going to substitute 3 again. We get 1 squared, which equals 1. So these two are not equal. So we can say that h of x is differentiable at negative infinity to 3 union 3 to infinity. The function is discontinuous excuse me, at x equals 3. Okay, so I can say it's discontinuous because remember, a function that is not differentiable to a point means it's discontinuous, but you can't say vice versa. Okay, so moving on to the next example. I know already you guys are not fond of piecewise functions, and they can be challenging. Not only do the limits of the slopes need to be approaching the same value, but the function must be connected and smooth, which is very important. So find the values of the constant a where the function is continuous over all reals. So we want to check that the limit as x approaches 3 from the left of f of x is going to equal the limit as x approaches 3 from the right of f of x. So we'll check that. Those two limits have to be equal. So we're taking the limit as x approaches 3 from the left of ax squared minus x, and that has to equal the limit as x approaches 3 from the right of 2a. So doing direct substitution, I'm going to get a times 3 squared minus 3 has to equal 2a, because that'll be a constant. So I get 9a minus 3 equals 2a. So I get negative 3 equals negative 7a. So 3/7 equals a is what I have. So now let's verify by checking, making sure that the function value and the left and right hand limits are all equal to each other. So starting with the limits. So if we take the limit as x approaches 3 from the left, we're going to have 3/7 times x squared minus x. And so we're going to have 3/7 times 3 squared minus 3. So we get 27/7 minus 3. So this will give us 27/7 minus 21/7. So we get 6/7. So that checks. And then when we take the limit as x approaches 3 from the right, we're just going to have 2a, and that's just a constant. So we have 2 times 3/7. So we get 6/7. So the limits equal each other, and f of 3 is a constant. It's just 2a. So this is going to be 2 times 3/7, which is 6/7 again. So we can see that it is indeed continuous when a is 3/7. Okay, next example. Show algebraically, using the ultimate form of the derivative, why g of x is not differentiable at x equals 1. So let's first check that for ourselves. Let's graph the function. So what we have here is we have a parabola where x is less than or equal to 1. So at 1 we are here, and then we're at 0, and then -1. So we have our parabola like that. If I can draw it a little nicer. There we go. Okay, and then we have the line x. So it would be here, and then here, and then here. So it would be like that. Okay, so we have kind of a weird little thing going on here, because if we were to draw the rest of the parabola, it's not going to match nicely along there. We're going to have like a little corner or a cusp. So we kind of have a cusp here. So let's see if that bears out as we show algebraically that this is not differentiable. So as x approaches 1 from the right, that's going to be our x function. We're going to do the limit as x approaches 1 from the right of f of x minus f of a, which will be 1 over x minus a. So that turns out to be the limit of a constant. So that's going to equal 1. And then when we do the same limit, as x approaches 1 from the left, we're going to take the limit as x approaches 1 from the left, and now we're going to use the x squared. So this is going to be f of x, which is x squared, minus f of 1, 1 squared is 1, over x minus 1. So we have a little bit of algebra to do here. So we get x minus 1 times x plus 1 over x minus 1. So we're going to have the limit as x approaches 1 from the left of 1, whoops, not 1 over, of x plus 1. So doing direct substitution, we get 2. So we can see that the left and right hand limits of the difference quotient do not match. So since the limit as x approaches 1 from the right of g of x is not equal to the limit, I guess I should put g prime of x, x approaches 1 from the left of g prime of x, because we're talking about the derivative here. G of x is not differentiable at x equals 1. All right, next topic, estimating derivatives of a function at a point. Now, some of you may be happy because we're going to use our calculators. So you might be able to use this on the calculator. So you might be asked to find a numeric derivative at a given point. So there's a function called nderiv on the 84 and derivative of point function on the Inspire. So the steps for doing it are right here and here. And I'm going to go through it real quick to show you on your calculator through the example below, which is what this problem is showing here, these two pictures. So I'm going to go ahead and go through and do this. So I'm going to pull up the 84 first. Oops. Pull up the 84 first. So what you want to do is you want to, let's see if I can put both of these on the screen at the same time. There we go. You're going to pull up just your calculator screen, and you're going to press the math button. So let me pull that up. So you press math, and it's right there, number 8. You can see it, nderiv. And then you pick what, you can use any variable, but it just makes sense to use x because you can just press the x button. You don't have to hit the alpha key or anything like that. And then the function is x squared minus 5x plus 6. And then over here where it's blinking right now, you put the specific value where you want to find the numeric derivative. So we're at x equals -3. So I'm going to type in -3 there, and you just hit enter, and it gives you the value of -11. Now on the Inspire, it's very similar. I've opened a calculator page. You don't need any special page, just your calculator page. And then you're going to press menu, and then there's a calculus menu, so you press 4, and it's the very first entry, numerical derivative at a point. So you press enter, and it's asking what variable you want to use. Again, you can use whatever variable you want. And then it's asking you what value, so you can hit tab. And again, we're at -3. We're doing the same problem. I think I put 2 negatives in there. Yeah, -3. And then you press OK. And then you get the same template on the screen that we saw with the 84. So you enter your function in, x squared minus 5x plus 6. And it already has the 3 in there for you. You can just hit enter and you get the same answer. Now we can verify that because we already know what the derivative is going to be. So you write it this way. If you're asked to write the answer, then you write, if it's a numerical derivative, you would write d dx of f of x, and then you put that you're evaluating this at x equals -3, and you write equals -11. And so I know that the derivative, because I did the derivative earlier, is 2x minus 5. So if I find f prime of -3, I'm going to get 2 times -3 minus 5. So I get -6 minus 5, which is -11. So it's a nice little trick to use if you need to find a quick derivative. Okay, so next example is just going through and doing this, but if you notice, I have a little caveat here that says explain any problems that you encounter. And what that is saying is there are times when this isn't the best way to do this. So if you get a weird answer, you might want to, if you have your calculator to begin with, you might want to graph it. So for instance, at the first one, we're at x equals 1. And if you know what this function is going to look like, then you can see why we're going to have a problem. So let me do it on the 84. So same thing, I'm going to do math. I'm going to choose number 8, and then I am going to choose my x, and then I'm going to put in the absolute value of x minus 1, and I'm doing this at 1. And when I do this, I get 0. But let's look at the function. So I have the absolute value of x minus 1. I'm zoomed in, so let me hit zoom 6. At 1 we're at the vertex, and the derivative does not exist there. So you have to be really careful, okay? The nice thing is I found that the Inspire is a little better at that than the 84, but not always. I mean, in the couple examples I have here, it is a little better, but there are functions that it doesn't work. So if I put in the absolute value, absolute value of why am I stuck here though? Hang on. Let me just start a new page. I don't know what I did there. Okay, so menu 4 1. So x, I want the value of 1. Hit OK. Okay. Oh, I see. I'm too far over. Okay, so I need to put in there ABS. See if it'll let me do it now. Do it this way instead of just pressing on it. Okay, there we go. X minus 1. And it tells you it's undefined. You even get a little warning sign there, which is nice. Okay, so you want to be real careful with your calculator sometimes. So this is actually undefined. So you guys go through the other two for your calculator, and I am going to tell you that all 3 of these are undefined at the point that I gave you. At 0 here, you're going to have a vertical tangent line. And here, you just have, you're at an undefined area of the function. And the Inspire worked out really nice, but on the 84 for both of these, I got, on my TI-84, I got f prime of 0 to equal 100. And for the second one, I got f prime of -2 to equal 0. So like I said before, I got an f prime of 1 here to equal 0. So you might want to be a little suspect. Whoops. You might want to be a little suspect here if your calculator gives you a derivative of 0, which you shouldn't be. But you'd want to double check it. Since you have your calculator, always just, if it seems like a weird anomaly, look at it on the graph and see if you do have one of those areas that the derivative would be undefined. So make sure it's doing difference quotients, your calculator, so you should analyze the graph as well. So I'm going to stop this video right here and finish it on the next one.